Hello guys, good evening. Can you hear me? Yes. So how was the last class? What all things you have done? Tell me what you did in the last class. No, I think Prabhat sir took the last class, no? Atomic size, I think we have done, no? I only have done that in last to last class only. Last class, Prabhat sir has taken the class. He must have done, the other stuffs. Or you revise the things in the last class. Okay, just a second. I thought I will be starting the next chapter today. We haven't done lanthanide. Acha, tell me, just answer me. Have we finished ionization enthalpy? No, just a second, not like that. Ionization enthalpy, okay, some of you are saying we have done. Okay, ionization enthalpy we have done. What about electron gain enthalpy? Acha, you tell me what have we done in the last class with Pravat sir? What was the last topic you were doing? Exception in size, I think I have already done it. Okay, so basically you haven't done anything new in the last class. It was a waste. Yeah, that's how it is. You didn't tell him that we have done it already? Anyways, fine. So I think, guys, let's stop this. I think so. We have done atomic radius, lanthanide contraction, and this thing, ionization energy. Okay, ionization energy. Anurag, we have done it. Others, like Anurag is saying, we have done it. What others? Pranav is saying he is not getting it in his notes. Is it? Acha. So most of you are saying okay. Okay, just give me a second. Hold on, everyone. Just a second, all of you. Hold. Fine. So, okay, so we'll start with ionization energy. Okay, write down the heading. Ionization energy. This we also call it as ionization enthalpy. Both are same thing. Definition you write down. Write down, it is the amount of energy required it is the amount of energy required to remove an electron amount of energy required to remove an electron from the outermost shell of an isolated gaseous atom. From an isolated gaseous atom. Okay, so any metal, any element M in gaseous state, if you provide ionization energy to this metal, it converts into monovalent gaseous ion and one electron goes out. copy this down. Just a second. Okay, from an isolated gaseous atom. That is ionization enthalpy. Okay, write down. Ionization enthalpy is always positive. It is always positive. Suppose you have an atom. I'm taking an example of sodium Na. Its electronic configuration is 1s2, 2s2, 2p6, 3s1. Okay. If you want to remove an electron from third shell, the outermost shell, the first electron you are removing, the energy required for this is IE1, the first ionization potential. This one is IE2, 3, 4, 5, 6, like that. Okay. So as you see, the successive ionization energy or enthalpy right, it is increases as we go from this to this direction. We are going towards the nucleus, closer to the nucleus. It is difficult to remove an electron. Then for any atom we'll write the successive ionization energy will write down in this order. IE1 is less than IE2, IE2 is less than IE3, and so on. Okay. As you go closer to the nucleus, the energy required to remove an electron is more. Yeah, correct. Generally, we provide energy in the form of heat or light. That's correct. Okay. Now, what are the factors which affects the ionization energy? So heading, write down factors affecting it. Clearly you can understand it that as the size decreases, ionization energy increases. So size has a factor, effective nuclear charge has a factor. More effective nuclear charge, more will be the attraction pull towards the nucleus, and more energy will be required. Right? Shielding and screening effect. Shielding or screening effect also we have a factor here. Right? So write down the factors affecting it. The first point you write down, Z effective. Z effective. Write down. As Z effective increases, as Z effective increases, the electron experiences more attraction pull towards the nucleus, hence attraction pull towards the nucleus, hence removal of electron is difficult. Electron is difficult. So we can write this as Z effective is directly proportional to the ionization energy, more energy required for the removal of electron. Okay. Right. That's why the trend is what? In a period left to right, ionization energy increases. General trend is this. Obviously, we have some exceptions, but general trend is this. Okay. Atomic size, the second factor we have. Write down as atomic size increases, the attraction pull towards the nucleus decreases, and hence the removal of electron is easier. So what we can write, atomic size is more, ionization energy is less. So inversely proportional to IE. Okay. So what is the trend here? You see, if you go top to bottom in a group, ionization energy decreases. And when I write ionization energy, it means we are talking about first ionization energy. That is understood. We'll discuss that. Second ionization energy successive, it is increases only, but there are some exceptions. We'll discuss that in exception. That's what I'm talking about. Anurag and Aditya. We'll discuss that. Okay. Yeah. That is the second point factor. The third one is penetration effect. Third factor you write down. Penetration effect of orbitals. One second. Write down. Ionization energy increases as the penetration effect of electrons increases in different orbitals. Okay, like if the electron is present in s orbital, its penetration effect is maximum. Like the order of penetration effect is s, then p, then d, and then f. And this order is based on the shape of the orbital. Spherical shape, we have s orbital, so it has the most penetration. Penetration means it is strongly attracted towards the nucleus. Okay, that is what the penetration is. Okay. Right. So this we discuss. These are the orbitals of the same shell. Orbitals of the same shell. For example, you see, suppose I'll ask you, compare the ionization energy of magnesium and aluminium. Tell me, which one has more ionization energy? Okay, magnesium. So the outermost electronic configuration of magnesium is 3s2, but that is for aluminium is 3s2 3p1. So s orbital has more penetration effect than p, then ionization energy of magnesium is more than to that of aluminium. This is the factor we have. Okay. Next one you see. The stability of, no, this is not an exception. This is the rule, penetration effect of this. S subshell and P subshell, S has more penetration, hence it is. No, it's not like that. You have, whenever you have a question, it's not like all the factors are applying, here. So they won't ask you question like this. Top to bottom will have a trend, right? Left to right, you can see according to the energy size, you can say. But yes, there are some exceptions here and there. We'll discuss that. Right. But here we have penetration effect. I'll come to this part again. Even if you talk about boron and beryllium also, I'll come to this part in the last. Let me finish these factors first. Okay. I have said there that left to right ionization energy increases generally, right? Remember, I have also mentioned there that there are some exceptions. Okay, some exceptions, some difference in the, some unexpected change in the trend we have. Okay, this is one of that where we have penetration effect. Okay, boron and beryllium also we have the same thing. I'll discuss that in the last. Let me first finish all the factors here. Got it? Fourth one you write down. Fourth one is the stability of half-filled, the stability of half-filled and fully filled orbitals. Write down the atom which has half-filled or fully filled configuration the atom which has half-filled or fully filled configuration is more stable is more stable and it's difficult to remove an electron from these configurations. These configurations means half-filled or fully filled configurations. Okay. In this, if you look at the trend here of ionization energy, D5 has minimum. Then we have P3. Then we have D10, P6. This is the order we have. Means one atom which has P3 configuration in the last and the other one which has D5. So the one which has P3 has more ionization energy. Okay. Now we'll see some exceptions in the ionization energy. Yes, D5 has higher than D3 because D5 is more stable. Okay, Pranav, just a second, Shreyash. I'll go back. Yes. Now look at this. First of all, we'll see trend in D block. In D block for group 3, the ionization energy follows this trend. 5D elements is the least, then we have 4D, and then we have 3D. For group 4, 5, 6, and 10, the order is 3D is minimum, then we have 4D, and then we have 5D. For group 7, 8, 9, 11, and 12, configuration is 4D is less than 3D is less than 5D. Okay, this is the order we have. 3D, 4D, 5D are the elements belong to this group. Like you see for group 3, the elements are group 3, you see the elements are scandium. After that we have yttrium, and then we have lanthanum. So this is 3D element, this is 4D element, and this is 5D element. So if they ask you scandium, yttrium, and lanthanum, okay, then the order of ionization energy, 5D has the minimum, so lanthanum is the least, then we have yttrium, and then we have scandium. Okay, copper belongs to which group? That is group 11, right? Right. So group 11, you see, the elements are copper, then Ag, and then Au. 3D, 4D, and 5D. So group 11 belongs to this. So 4D has the list, okay, least, okay. So Ag minimum, then we have 3D, so it is copper, and then we have Au. Clear? Reactivity series is not related with ionization energy, Pranav. It is an electrode potential. It is not this. Got it, Pranav? It's not only for the gases. The state of the atom should be the gaseous state to remove an electron from the gaseous state. It is not decided on the basis of last cell. See, the thing is what? we are doing this particular thing under exceptions. Okay. So we do not have only one factor here. There are many factors, like top to bottom. If you go, size generally increases, correct? But at the same time, the electrons in the inner shell also increasing. That produces repulsion onto the outermost shell, right? So there are many factors. The overall trend we get in this way, this combines the all factor we have. So if you think of only one factor, the order should be what? Suppose I'll take only the size factor. Down the group, size decreases. Then AU should be least, CU should be max. But that is not the case, because only size factor is not here. There are multiple factors. If remaining electron requires more energy, see, Pranav, these are the two things you're talking about. You're talking about reactivity of an atom plus ionization energy at the same time. Okay, I can say that the ionization energy of gold is more than to that of copper. Then I can say that gold is less reactive than copper. Relatively, we can say. But if you try to remove an electron from gold, copper, and Ag, then we'll say no, that this is the order of ionization energy. So reactivity is the different thing. Removal of an electron, ionization energy is different. Based on ionization energy, we can conclude the reactivity of it, right? Activity series that you are talking about, that series is not based upon the ionization energy, but that is the electrode potential of an atom, of a metal. Yes, so down the group, size increases in general, right? There are some, factors like inert pair effect, lanthanide contraction, transition contraction we have. So all these factors collectively, combinedly, collectively they gives this. These are the orders of various groups here. That's why we are doing this under exceptions. If you go with only one, factor, then maybe you get different answers. But the thing is, like I said in the beginning only of this chapter, that there are multiple factors. Okay, and the overall trend that you have, it is the combined effect of all these factors. So whether you know at what point what factor you have to apply, or if you know this order, you can do this directly. So till now, the question that they have asked about this scandium, yttrium, lanthanum, copper group. This question they have asked once. Okay, and there is one more trend we have into this, I'll tell you, and that trend is titanium, zirconium, and hafnium. Which group is this? Ti, Zr, and HF. Group 4, right? So group 4 element, you see, we have titanium, we have zirconium, and we have hafnium. Between lanthanum and hafnium, what is the element present? Between lanthanum and hafnium, how many elements are there? 14. Because between these two, we have lanthanides present, right? So that's why in HF, they experience a very weak shielding effect of F subshell. That's why the size of hafnium is extremely less, or it has the unexpected size because of lanthanide contraction, correct? So the correct order here is 3D is titanium. You see group 4 is here. Titanium is the least. Then we have 4D. 4D is zirconium, and then hafnium. Hafnium is little higher than zirconium. We can also say it is almost equal, the size of hafnium and zirconium. Why the size is equal here, or the difference is not that great? It is only a bit higher than that of zirconium, the ionization energy, right? That is because the lanthanide contraction over here. Okay, so ionization energy is almost very much similar to that of zirconium, but mostly if you have to choose between this one and this one, we'll go by hafnium has more this thing ionization energy than zirconium. That is because of lanthanide contraction only. Okay, so this one is also important, the order that they have asked in the exam. Basically, for D block, if you remember these three things, you can answer all your questions. Okay, that's the one thing. Now, second thing, like I said, there are multiple factors which affects the ionization energy. This particular thing you can understand with this example. See this one, the second one here. Write down, all of you. For the same element, to decide the ionization energy, we consider only charge factor comma, the electronic configuration is not considered. The electronic configuration is not considered. Okay, what do you mean by this? I'll show you this. See, we have three elements and ions of it. For example, we have nitrogen, we have N plus, and we have N minus 3. Okay. So if you look at the electronic configuration, what is the outermost electronic configuration of N? Just a second, Pranav, we'll discuss that. Wait. The outermost electronic configuration of N is 2s2, 2p3, right? For N plus, it is 2s2, 2p2, and N3 minus is 2s2, 2p6. Could you tell me the ionization energy with respect to this P3, P2, and P6 configuration? Which one has the maximum ionization energy? I have given you that half cell configuration. The maximum ionization energy we have for, yes, we have for N minus 3, P6 configuration, then N, that is P3 configuration, and then N plus. Right? This is according to what? According to EC, electronic configuration. Correct? This is the one factor. If you consider electronic configuration, you will get this as the answer. Now, if you talk about here the size of an atoms or ions, which one has the maximum size? Maximum size is for N3 minus, and N plus has the minimum. then N, and then N plus. Okay. So the ionization energy with respect to size, if you consider, it is maximum for N plus, then N, and then N3 minus. So you see, we are getting exactly opposite order over here. So point I am trying to make is what? That if you consider electronic configuration, you'll go by this answer. If you consider size, you'll go by this answer. So these two, size and EC, electronic configuration, are contradictory to each other. Right? They are contradicting to each other. That is the point I'm trying to make. That here we have multiple factors. Overall, the effect that we have, the order that we have, it is the combined effect of all these, or depends upon the factor which is dominating here. So what is the rule here? The rule is when we have the same element or its ion, then we do not consider the electronic configuration, but we consider what? But we consider the size factor we consider. Okay, this is the rules we have. So this one is wrong. This one is wrong. It is not correct. Ionization energy is this. Did you get my point? Tell me, any doubt? Okay. Now, another important one, boron family, the third one, group 13, boron family. What is the order of ionization energy here? The order is as we go down the group, the ionization energy decreases. As size increases, so boron, aluminium, then gallium, then indium, and then thallium, right? But again, this order is also not correct. The correct order here is, you need to memorize 1, 5, 3, 2, 4 in decreasing order, right? In descending order. First one means first element, boron, maximum. Fifth element, thallium. Then third element, gallium. Then second element, aluminium. Then fourth element, that is indium. This is the order we have here. Why we have this trend? This gallium is more because of transition contraction. Transition contraction, D block elements. Thallium is more because of lanthanide contraction. Size decreases and hence ionization energy increases. This is because of so this is what you have to memorize here. No, indium is not second. No, the factor I have written, no, transition contraction, lanthanide contraction. So there are many things. It's not a one particular factor here. Pranav, tell me. Boron is greater than aluminium. That's what we have here also. Boron is greater than aluminium. Yes, lanthanide is more dominating because F shows weaker screening effect than D. This one you're talking about? One, 5, 3, 2, 4 you're considering? This number is the position of elements. Like 1 is the first element, boron. 5 is the fifth element, thallium. 3 is the third element, gallium. Second element, fourth element. Yeah. Similarly, we have a small change in carbon family also, group 14. For carbon family, the correct order of ionization energy: carbon, silicon, then germanium, then we have lead, and then we have Sn in the last. So here we have a change, right? This change, could you tell me the reason for this? The reason is lanthanide contraction. Yeah, the reason is again here lanthanide contraction. Okay, so these are the some exceptions we have. Apart from this, if you compare like beryllium and boron, beryllium, the configuration is 1s2 2s2, and beryllium is boron is 1s2 2s2 2p1. So beryllium has more ionization energy than boron. Okay, if we talk about nitrogen and oxygen, so 1s2 2s2 2p3, 1s2 2s2 2p4. Nitrogen has more ionization energy than oxygen because of half filled T3 configuration. Got it? Yes, if there are more than one effects, see, if you have charge and length factor, then mostly we consider charge there. But logically, you cannot say always. Okay, you should know which effect is dominating here. That you have to memorize. Okay, but charge and length, charge dominates always. No, fluorine and nitrogen is not the case here. Nitrogen is more than to that of oxygen, but in case of fluorine, the size is small. Fluorine, the outermost electron experience more attraction towards the nucleus. Plus, fluorine is the electronegative element also, most electronegative element. So fluorine does not want to lose its electron. Rather, it has tendency to accept electron and gain the inert gas configuration. Right. So to remove an electron from from fluorine, it requires very high energy. Okay. So these are the few exceptions we have discussed. Must memorize all these things that we have discussed. Important. Okay. Now, ionization energy, when we talk about, we'll talk about the tendency to lose an electron, right? And tendency to lose an electron is nothing but the metallic nature of an element, correct? So this is the application of ionization energy. Write down the heading, application of IE, ionization energy. What all things we can conclude from ionization energy? You see, ionization energy is more, then it is difficult to remove an electron, right? Means ionization energy is inversely proportional to the basic nature of oxide. Bn is the basic nature. Write down in full here. Bn is the basic nature, right? Ionization energy is more, then metallic nature is less, inversely proportional to metallic nature, and it is also inversely proportional to the oxidizing tendency of the element. Okay, I'll write down here. Bn stands for the basic nature, right? Mc stands for metallic nature, and Ot stands for oxidizing tendency. Oxidizing tendency. Yes, you can say that, Anurag. When an atom is releasing electron, we say it is going under oxidation. So what we can say, left to right we go in a periodic table. Ionization energy, we know it increases left to right, and hence the metallic nature decreases. Basic nature decreases. Oxidizing tendency decreases. In this, only one note you write down. basic nature of oxides is inversely proportional to its ionization energy. So we know this fact that top to bottom we go, ionization energy decreases. Ionization energy decreases means the basic strength of oxides increases, and when basic strength increases, we know that acidic strength decreases other way. Similarly, left to right if you go, we know ionization energy increases, and when ionization energy increases, basic strength decreases of oxides, and when basic strength decreases, the acidic strength of oxides increases. Okay. Based on this only, two questions they have asked in JEE. Write down the basic strength of these oxides, Na2O, then we have K2O, and then we have CS2O. Basic strength order you write down. Basic strength order of this: Li2O, BeO, B2O3, CO2, and 2O5. Right? So on the basis of this information, we can say the order is this. Here also left to right we are going. The basic strength order is this. Oh, sorry. Left to right decreases. So this would be the acidic strength. Basic would be the opposite of it. This is the basic strength of oxides. No, this is the oxides. It is not the atom. This is not beryllium, guys. This is BeO. For oxides, I have written here. Left to right, ionization energy increases, basic strength of oxides decreases. It is not an atom, it is there in the bonding state. Right, so for bonding state, we have like this left to right. If you go, basic strength decreases, acidic strength increases, hence the order is this. Right, for atom it is fine, beryllium and boron. It is in the bonding state. Okay, so these are the applications of ionization energy. Okay, now we have some facts about ionization energy and electron uh, gain enthalpy. Okay, so we'll discuss that after finishing electron gain enthalpy. Some facts we'll see, right? After this, the next term you write down, electron gain enthalpy. Electron gain enthalpy. Electron gain enthalpy is represented by this delta Eg, electron gain H negative. This is electron gain enthalpy. Okay, write down into this. Write down, when an electron is added, when an electron is added to a neutral isolated gaseous atom, to convert it into a negative ion. When an electron is added to a neutral isolated gaseous atom to convert it into a negative ion, the enthalpy change or the change in enthalpy takes place in this process is defined as electron gain enthalpy. Done? Write down next line. It can be endothermic or exothermic. It can be endothermic or exothermic. Anything is possible. Negative or positive. Okay, can be endothermic or exothermic. See, mostly what happens, you have an atom A, and you're trying to, gaseous atom A, trying to add an electron onto this. Then it converts into a negative ion, Ag minus. Okay, so in this process, in general, what happens, energy releases. Energy releases. But not always. There are some cases in which the energy is getting consumed. Okay, not always. Okay, generally bond formation is an exothermic process. Whenever A and B bond forms, some amount of energy comes out in this process, releases. Right? Now, another thing, write down, more negative, this point is also important, more negative electron gain enthalpy means more negative electron gain enthalpy means more tendency to accept an electron is more, right? Negative means what? That the energy releases. Right? Negative delta Eg H, if it is negative, means energy releases. If it is positive, means energy provided into this one. Right? When we compare the electron gain enthalpy of two atoms, we just compare with the magnitude. Sign we won't consider here, because sign just represent that whether it releases, the energy releases or gets consumed into this particular process. Correct? We only consider the magnitude to compare the electron gain enthalpy of an atom. More negative electron gain enthalpy means more energy releases in that particular process. Okay, so that is what the thing is. Now, next time you write down, electron affinity of an atom. Another line you write down, electron affinity of an atom is the tendency of an atom to accept an electron. How easily an atom can accept electron is the electron affinity of that atom. Okay. It is a tendency of an atom. Yeah. Electron affinity is a tendency of an atom to accept an electron. So one thing you understand here, if electron gain enthalpy is negative, electron affinity is positive. It goes other way. Okay. So write down the next line. If energy is released, if energy is released when an electron is added to an atom, when energy is released, if an electron is added to an atom, the electron affinity is taken as positive. Okay, if energy is released when an electron is added to an atom, the electron affinity is taken as positive. The relation of this, you write down the next thing, just this relation you write down. The electron gain enthalpy delta Eg H negative is equals to minus of Ea electron affinity minus 5 by 2 R T. This is the relation we have. Okay. One last point in this you write down. Electron affinity is defined at absolute zero temperature. Absolute zero temperature is minus 273 degrees Celsius. That is 0 Kelvin. Okay. Just one thing you have to take care of here, that electron gain enthalpy is the amount of energy released when an electron is added to an isolated gaseous atom. Okay. More negative electron gain enthalpy means more amount of energy releases. Ease of adding an electron is more over there. Okay. Negative sign represents that the energy has been released. Positive sign represents that the energy has been provided to add an electron on an atom. Okay. Now, next write down the factors affecting electron gain enthalpy. Factors affecting it. The first point is size of an atom. RT is, R is the gas constant, T is the temperature. PV is equals to nRT. Okay, so write down quickly this, taking a lot of time into this one. Whether you talk about electron affinity or electron gain enthalpy, electron affinity or electron gain enthalpy, it is inversely proportional to the size. Because if the size is more, addition of electron will be difficult. Inversely proportional. In general, we have some exceptions, we'll see that. Okay, effective nuclear charge, the second one. The second one is Z effective. As Z effective is more, addition of electron will be easier. Okay, so Z effective and electron gain enthalpy. Z effective is directly proportional to the energy release in this process, that is electron gain enthalpy, negative charge. Okay. Next, write down electronic configuration. Electronic configuration. Write down the elements with half filled. EA is opposite of delta. I'll tell you, just this point you write down, Himanshu will explain that. Write down the elements with half filled or full filled orbitals the elements with half filled or full filled orbitals are more stable half filled and full filled orbitals are more stable and they do not take up electrons easily and they do not take up electrons easily. Hence, the energy is required to add an electron Hence, energy is required to add an electron on these configurations. Okay, so for example, if you talk about nitrogen and phosphorus, to add an electron on nitrogen, you see it has configuration 2s2 2p3 and it has configuration 3s2 3p3. The electron gain enthalpy for phosphorus is minus 74 kilojoule per mole, negative value here. But here the energy is required to add an electron, plus 20 kilojoule per mole. So under these cases, you see the electron gain enthalpy may be positive. But when we compare the electron gain enthalpy for the two atoms, we don't see the sign over here, and we say the phosphorus has more electron gain enthalpy. We only compare the magnitude. No, we are not creating enough instability. The thing is, the atom is quite stable because of its half filled or fully filled configuration. These atoms do not want to take up any electron and go towards instability. So if you want to add an electron, you have to push that electron onto that atom. And for that, you require energy. This is the electron gain enthalpy, right? So if electron gain enthalpy is positive, then electron affinity is negative. Okay, electron affinity is negative there. Okay, so electron affinity of nitrogen is more than to that of phosphorus. Got it? Himanshu, did you get it? Electron affinity and electron gain enthalpy. These two are opposite in terms of their sign. If electron gain enthalpy is negative, electron affinity is positive, and other way. Okay. Similarly, you see halogens like suppose chlorine. Fluorine, it has 2s2, 2p5 configuration. So fluorine or halogens have high tendency to accept electron and converts into a negative charge ion because it becomes stable because of this fully filled configuration. So it has very high tendency to accept an electron. So its electron gain enthalpy and electron affinity is very high and negative values. Write down this point. For halogens, or simply write down like this, halogens have high tendency to accept an electron just a second, Aditya. Halogens have high tendency to accept an electron and forms negative charged and forms halide ion and forms halide ion. Hence they have very high negative value of electron gain enthalpy. Hence they have very high negative value of electron gain enthalpy. I said in the first part that halogens have very high tendency to accept an electron and forms the halide ions and forms halide ions and forms halide ions, and hence they have very high value of very high negative values of electron gain enthalpy. Very high negative values of electron gain enthalpy. No, Anurag, it's other way. High negative value means what? -10 and -20. So -20 is higher negative electron gain enthalpy. Right? With negative sign, the value is very high. Means minus 10, minus 20, minus 40, minus 60 if you say, then minus 60 has very high negative electron gain enthalpy. Okay. No, it's not. Halogens has 2p5 configuration, so they will easily accept that one electron. And since they are gaining the noble gas configuration, so they releases a lot of energy into this. Just a second, Nishant. Okay, it has high tendency to accept an electron since they gains noble gas configuration, hence they releases a lot of energy into it, hence negative electron gain enthalpy. Nitrogen and phosphorus we'll discuss. We'll discuss just a second. We'll discuss that. See, first of all, you try to understand this, that electron affinity and electron gain enthalpy, these are opposite. If electron gain enthalpy is negative, electron affinity is positive. So phosphorus has high electron gain enthalpy, you see, 74. Nitrogen has 20. So electron affinity of nitrogen is minus 20, and that of phosphorus is plus 74. No, electron gain enthalpy is the energy released. You see the definition. Why phosphorus has more? You can also understand this way. See, actually what happens, I'll tell you. That's why I've given you the theory for this, the notes properly. I have dictated you each and every line, because this is a bit confusing because of sign over there. Actually, suppose you take an example of fluorine and chlorine. So fluorine and chlorine, obviously the size of fluorine is smaller than to that of chlorine. Okay, so the configuration you see for fluorine is, it is 2s2 2p5, and this is 3s2 3p5. Okay, size of 3p is bigger than that of fluorine. So this has 5 electrons, right? 1, 2, 3, 4, 5 electrons in this shell. Just a random representation I'm telling you. And here also the 5 electrons we have like this. Now, since the size of chlorine is higher than that of fluorine, and you want to add an electron to these atoms, right? You want to add an electron to these atoms. So which one produces more repulsion to the coming electron? Fluorine or chlorine? Which one? Fluorine, because the fluorine size is small, it is compact, and the electron, the 5 electron is distributed on a small region, right? In case of fluorine, right? But the surface or the volume of chlorine is more, then the electron is scattered there. In case of chlorine, they are not concentrated. In case of fluorine, it is more concentrated relatively, correct? So fluorine present more repulsion to the coming electron. right? Hence, it is difficult for this electron to add on chlorine, on fluorine, correct? Hence, what happens here, due to the large size of chlorine atom, the incoming electron experiences very less repulsion, right? And that is why the electron gain enthalpy of chlorine is more, right? This happens in second and third period of element. Like for the same reason, I can also say, like the reason we have for fluorine and chlorine, same reason we have for nitrogen and phosphorus, same reason we have for boron and aluminium, same reason we have for oxygen and sulfur. Okay, this is what the thing, we have larger size, lesser repulsion, easier to add an electron, more energy releases. Okay, so in this one we have a very important trend. I'll tell you that a bit later. Okay, one more point here, you write down the electron gain enthalpy of noble gas the electron gain enthalpy of noble gas is positive since they are highly stable, highly stable, and we need to provide energy to add an electron on these atoms. We need to provide energy to add an electron on these atoms. Done. Okay, so for halogens it is positive electron gain enthalpy, for nitrogen also it is positive, but for all other elements the electron gain enthalpy is negative. Okay, this point you must remember. Halogens, sorry, noble gas it is positive, nitrogen it is positive, for all other elements it is negative. Okay, yes, if it is positive means it has less tendency to take an electron. We have to push that electron on the atom, and for that we need energy, hence it is positive. For the noble gas, I said it has highly stable configuration, and hence we need energy to add an electron on these atoms. And hence the electron gain enthalpy is positive. We have to provide energy here. Got it? Okay. Just a second, Madhav. Okay. So what you have to keep in mind that for noble gas and nitrogen, it is positive. Okay. Trend you see here. Trend of electron gain enthalpy. First point, down the group, top to bottom, the electron gain enthalpy decreases. Decreases means it becomes less negative, means magnitude is decreasing. Magnitude is decreasing, less negative is with minus sign, the value we are considering here. Left to right in a period, delta Eg negative increases, means it becomes more negative. It becomes more negative. Okay. For halogen family, you see, the trend of electron gain enthalpy, chlorine has maximum, then fluorine, then bromine and iodine. This is very, very important. They've asked this question many times in the exam. Chlorine has maximum electron gain enthalpy here. Okay. Now, like I said, some facts and some concepts of this you must remember. Like, you see this, the electron affinity order. Electron affinity order. It is minimum for neon. I'm talking about group 2. Then we have nitrogen. Then we have beryllium, boron, lithium, carbon, oxygen, and fluorine. Right? Neon, you see, neon is the noble gas, it is positive. Nitrogen also positive value. So we have to provide electron energy into this. Right? And this is the order we have electron affinity. Okay. If we talk about the maximum electron affinity, maximum EA, electron affinity, it is for the most reactive, all these you have to memorize, okay? Most reactive non-metal. Most reactive non-metal is chlorine, maximum electron affinity in the periodic table. Minimum ionization energy. Minimum ionization energy is for most reactive metal, and most reactive metal is cesium. Okay, all these questions they have asked. If you talk about the maximum ionization energy and minimum electron affinity, this is for the most unreactive most unreactive non-metal, and that is inert gas. Okay. Group 17 I have given you already. Group 16, you see, the order of electron affinity is sulfur, then selenium, then tellurium, and then oxygen. The electron affinity of iodine is more than to that of sulfur. The electron affinity of chlorine, which is the maximum, it is even less than the ionization energy of cesium, which is actually minimum. Copy it on this. No. See, guys, I'll tell you one thing. Magnitude of energy is the amount of energy released or consumed. Okay. The negatives or positive sign, it just represent whether the energy is being provided or the energy is being released. So negative value means that the energy is getting released. Positive value means the energy is getting consumed. Just a convention. The magnitude written with negative sign means that is the amount that has been released. Okay. Why is it so the hydrochloric acid is stronger than HCl? Why do you want to know this now, Shreyash? That is not the topic we are doing, no? But since you have asked, I'll tell you. HF and HCl, fluorine is the more electronegative element. So F minus is more stable than Cl minus, the conjugate base. By the way, the answer is opposite actually. I have discussed this example in the class, maybe you don't remember. Just a second, Anuradha. If you see the acidic behavior of HF, HCl, HBr and HI, then it is maximum for HI and minimum for HF. Because of the stability of I minus. So it is other way actually. HCl is a better acid than HF. Yes, Cl minus size of I, correct. Similarly, the size of Cl is more than to that of fluorine, so that is more stable than F minus. Okay. So these are the points you must remember for this electron affinity and ionization enthalpy. Okay, the next thing, the next term we have to discuss, write down, that is electronegativity. Yeah. Heading, write down electronegativity. Write down, it is the ability of an atom it is the ability of an atom to attract the shared pair of electron. It is the ability of an atom to attract the shared pair of electron. It is always defined in a bonded state, right? For absolute atom, it is not true. In a bonding state, we can define this. So you see, suppose we have a bond A and B, right? So what it means, if B is more electronegative than A, then what happens? Electronegativity of A is lesser than to that of B, correct? Then the pair of electron that we have here, it is shifted towards B, the more electronegative element. And hence it becomes delta negative, it becomes delta positive. So it's like a tug of war for these two electrons between A and B. The one which is more powerful, that will drag the electron towards its side. This ability of an atom to drag the shared pair of electron. Shared pair means the pair of electron which is present in the bonding state. Like this is the bond lone pair, this is shared pair of electron in a bond, right? NH3. So the pair of electron that is present in a bond, that is the shared pair of electron. Okay. So electronegativity, we have factors here, many factors you see. Like the first one, as Z effective increases, electronegativity increases. Remember, I have discussed this in GOC also. Yeah, it is the opposite of electronegativity. Okay, we can say that electropositivity. Okay, this is the first factor. Second one, as atomic radius increases, electronegativity decreases. Why it decreases? Could you tell me? Why is this order we have? Because the distance is more, right? Nucleus and the electron distance is more, and hence the electronegativity decreases. Third one, as the positive charge on atom increases, on atom increases, electronegativity also increases because it attracts the electron. For example, we have carbon, nitrogen, and carbon, nitrogen, positive charge on it, plus. So here the electronegativity of this nitrogen is more than to that of this nitrogen because of positive charge we have here. Okay. The fourth factor we have the state of hybridization. State of hybridization. Hybridization we know as, write down, percentage S character increases electronegativity increases. And hence we say sp hybridized carbon is more electronegative than sp2. It is more electronegative than sp3. Remember this thing we have discussed in GOC also a little bit. Yes or no? Right. Now the trend of this you see, left to right if you go, electronegativity increases. Fluorine is the most electronegative element. Most electronegative element. Top to bottom if you go, electronegativity decreases. Okay, write down electronegativity of gallium. I'll learn this way. Gallium is more electronegative than aluminium. Similarly, germanium is also more electronegative than silicon. Okay. We can also calculate electronegativity Yeah, decontraction is correct. NaCl is, see, Anurag, NaCl is an ionic compound, right? So there we have two ions, Na plus and Cl minus. Okay, so it is an electrostatic attraction between Na plus and Cl minus. We don't have a bond like, HCl or any other molecule, HF, like that. Okay. You see, we can also calculate electronegativity, but calculation based question they won't ask you. But since it is given in the syllabus, we'll just see the formula. Okay. Hardly you will get question on this. Okay. So calculation of electronegativity, the first one we have, we call it as Pauling's scale. For this one, the change in electronegativity or the difference in electronegativity between the two atom A and B we have, it is 0.208 root over of delta AB. What is delta AB? Delta AB is the resonance energy. Resonance energy, which is calculated by this formula. EAB minus root over of EAA into EBB. Okay, EAB is the bond energy Okay, EAB is the bond energy of AB bond. Of AB bond. Similarly, EAA is the bond energy of AA bond and BB is the bond energy of BB bond. Did you get it? So obviously you see this formula. Suppose if you remember the formula also, if bond energy is not given, you won't be able to find out the difference in electronegativity. That's why these kind of questions they won't ask. Okay, not important. But just a formula we have, I have given you, that is it. Okay, got it. So this fluorine, the electronegativity is 4. That is according to the Pauling scale. No, it's not. Polar covalent is something else. Ionic is something else. Anurag. Polar covalent bond is HCl. Because of high electronegativity of chlorine, the bond is covalent, but the electron pair is shifted towards the chlorine. And that's why we have some polarity develops here. And that's why it is polar covalent bond. No, Na plus will attract, but it is an electrostatic attraction. Na plus and Cl minus, when these two comes closer, we'll have an electrostatic attraction between the two. And that is the ionic bond we have here. Understood? No, it's not. HCl is not electrostatic. It is because of, it is similar to H2 and HCl if you see. If you compare H2 and HCl, in H2 we do not have electronegativity difference. So electron pair will be there at the center of the two nucleus. But HCl, chlorine is more electronegative. So the bond pair of electron is slightly shifted towards the chlorine. And that leads to the polarity in the bond. So hence it is covalent, polar covalent bond. Understood, Anurag? Okay, so this is it. Now, according to Pauling's scale, the order of electronegativity, fluorine has maximum electronegativity, then oxygen, then nitrogen. These three you must remember. Then we have chlorine, bromine, iodine, sulfur, carbon, and then let it be. First three you must remember, the most electronegative element. Okay. Now, one more thing just before the break. One more formula we have by which we can calculate the electronegativity difference. We call it as Mulliken scale. Mulliken, Mulliken scale. Mulliken scale is basically the average of ionization potential and electron affinity. This divided by 2. IP is the ionization potential, ionization energy, and EA is the electron affinity. Done? Okay. The next is the application of electronegativity, and the application part we'll discuss after the break. Okay. So write down the heading just application. We'll discuss it after the break. So application we'll discuss, then we'll discuss dipole moment, polarization. All these things we'll see after the break. Take a break, guys. We'll resume the session at 6:30. Okay. Take a break. Hello. Okay. Now the next thing is the application of electronegativity. The first one is what? We use this electronegativity term for naming a compound, right? First point to write down. Write down. In a compound, the name of, in a compound, the name of more electronegative atom hello, can you hear me? Yes, write down. In a compound, the name of more electronegative element is written at the end with "ide" suffix. More electronegative atom is written in the end with "ide" suffix. So for example, if I have IBr, so bromine is more electronegative. The name of this compound is iodine bromide. Iodine bromide. "Ide" suffix will add into this in the last. Okay. OF2, oxygen difluoride. Fluorine is more electronegative. Oxygen difluoride. Of the bond. Write down. See, in a bond, if difference in electronegativity, suppose we have a bond AB, write down like this notation wise. If the difference, delta means change in electronegativity, difference of AB is less than 1.7, then the bond is said to be, then AB is covalent bond. Right? If it is more than 1.7, then this bond is ionic bond. Covalent bond, ionic bond. Okay. We have one exception into this. HF, if you see the molecule HF, the difference in electronegativity for HF, you see, fluorine is 4 and hydrogen is 2.1. This is a value I'm telling you. It is 1.9. So it should be what? It should be ionic, but it is covalent in nature. It should be ionic according to the logic above written, but it is covalent bond. Okay, this you must remember here. Okay, one more thing you see, none of the bond can be completely, that's the same thing. Values will find out from the two formula. You don't have to memorize the value. They won't ask you this. Okay, so don't worry with the value. For this one, I have just given you for this to understand this. Okay. Any bond can never be completely covalent or can never be completely ionic. When I say the bond is covalent, means its covalent character dominates. Okay, ionic character is less. That is what it means. The same thing also we have in ionic bond. Okay, so how to measure the covalent character in ionic bond or ionic character in covalent bond? Okay, so we can calculate the percentage ionic character in a covalent bond with this formula. Again, all these calculations are not important. Okay, write down the third application. Ionic character in covalent bond. Ionic character in covalent bond. Write down as difference in electronegativity increases, as the difference in electronegativity increases, delta En means difference in electronegativity increases, it leads to the ionic character in the molecule. Ionic character also increases. How do we calculate the percentage ionic character in a given bond? The percentage ionic character we can calculate by this formula: 16 into delta En plus 3.5 into delta En square. What is that, Pranav? Dipole moment it is. Okay, we'll discuss that. Wait. This is the formula of percentage ionic character. Not that important, but you must write it down. Hardly you will get one or two questions on this. In a chapter, when you solve the questions, no, hardly you will get one or two. So not that important. This is ionic character in covalent bond. So as the percentage, as the difference in electronegativity increases between the two atom in a bond, their ionic character increases. And percentage ionic character we calculate by this formula. Okay, fourth one we have bond strength and bond length. Bond strength and bond length. As the difference in electronegativity increases, bond strength increases. And when bond strength increases, it means bond length decreases. Bond length decreases. You know, smaller bond has more strength, right? So bond strength increases, bond length decreases, or vice versa. Bond length increases, bond strength decreases. It goes like this. Right? On the basis of this only, we can also explain the acidic behavior of these compounds. HF, HCl, HBr, HI. Tendency to lose H plus is acid. So HI has the maximum bond length. Hence bond strength is minimum here. Can easily lose H plus ion. And hence the acidic order is this. HI is the most acidic compound among these. Acidity increases. So these are the applications of electronegativity. Done. Okay. The next term we'll see is write down dipole moment. Dipole moment is the characteristics of a dipole in any kind of field, electric field or magnetic field. What is a dipole? Dipole is something like when we have two charged particles placed at a distance, positive and negative, Q1, Q2. Positive charge, negative charge. When these two charged particles present at a very small distance, then this behaves as a dipole. Suppose the distance is d here. Two pole we have, one is positive, other one is negative. So it is a dipole. So when an electric field it is present over here, then electric field, suppose it applies the force on the positive charge in downward direction. So on the negative charge, it is in opposite direction, that is upward, like this. And hence it has tendency to rotate in this field like this, which creates a moment here. That is a dipole moment we have. I said what? Dipole is when we have two charge, opposite charge, positive and negative, present at a very small distance, d, right? Then this thing behaves as a dipole because you have two pole, one is positive, other one is negative, right? So this dipole okay. So however, it is a part of physics here, but little bit I'll explain you here. This is not required in chemistry when you are solving questions for this. Okay. Yes, any two opposite charge we have here, opposite charge particle, plus and minus. So if any electric field or magnetic field is present, so suppose if this exerts a force in downward direction like this on positive charge, so obviously in negative charge, the force will be on the opposite direction, right? And hence we'll have a torque here, which rotates the two charges in this direction, the arrow I have given here. Because of this rotation, there is a moment in this particular uh, charge that we have. This thing we generally discuss in physics, the moment and all. Here in chemistry, you don't have to calculate the dipole moment. Just you need to know the two charges present and whether there is a dipole moment or not, net dipole moment. So how do we do this? I'll tell you here. Dipole moment is represented by mu. This is the dipole moment mu, and it is a vector quantity. You must have studied vector and scalar, right? What is a vector? What is a vector?
So
Uh,
force with direction.
Magnitude and direction, both. Any example of vector?
Acceleration.
Velocity, force. Okay, fine. So dipole moment is also a vector quantity, and it also follows the rules law of vectors. Okay, addition law of vector that we have. Direction of dipole moment is from positive to negative. From positive charge to negative charge. Now, what is the role of this here in chemistry we have? Again, I'm telling you, we are not going to calculate the exact value of dipole moment. Okay. We are just going to check whether the molecule has a net dipole moment or not. That is it. Okay. So, for example, suppose I have taken HCl. So, HCl is this. How this bond, HCl bond, behaves as a dipole here, you see. Chlorine is more electronegative, so it has delta negative charge because it will drag electron towards this side. And this becomes delta positive. And we have some bond length D here, right? So obviously you see the two charge plus and minus present at a distance D, this behaves as a dipole here. So here we have a dipole moment from positive to negative direction, and that we can show like this. Like this will show the dipole, the vector here. An arrow and a cross at the tail. No. I just talked about this moment here, dipole moment. Okay. But yes, whenever you have this, it has tendency of behaving as a dipole, and hence it will have a moment. Generally, we define this rotating tendency when we have the force exerts onto this part, positive and negative parts. That's why I have explained this. Here we don't require any, any force over here. But yes, if it is there, then this will have a dipole moment. Basically, it is a separation of charge, and with that movement of electrons, right, there will be dipole moment. Okay. We cannot say this that there is electric field is not present, then how dipole moment we define? Because electrons, with electrons also there are electric and magnetic field associated. The electron is a wave particle, correct? So with the electron also electric and magnetic field associated is there. Yeah, it will have the tendency to rotate like this. Depends upon what force, what magnitude of the force is, but it will have this kind of force. Okay, so electron is this positive and negative charge that develops because of the movement of electron itself, and there are electric and magnetic field associated with electrons, and hence we can consider here also a dipole moment. Yes, we can say that, Anurag. Wherever we have charge separation at a smaller distance, we can talk about dipole moment. Now the application of this you see. In this, do we have a net dipole moment? In this, do we have a net dipole moment? Mu net is not equals to 0. We can say that. Okay. Another example you see. I'll take H2O. Oxygen is more electronegative. So oxygen has delta negative charge. This has delta positive charge, delta positive charge. And because of this charge separation, we have, just a second. This charge separation, we have a dipole moment in this direction, positive to negative. And we have a dipole moment because of this bond in this direction, positive to negative. And these two dipole moment has a vector quantity, so we'll have a net dipole moment in this direction, mu net. H2O also have net dipole moment does not equals to 0. Did you understand it? Okay. So how do we define dipole moment? Mathematically, dipole moment is defined as mu vector. It is the product of the charge Q into the distance between the two charge from positive to negative. This is the mathematical definition of dipole moment, Q into D. So it depends upon the charge plus the bond length. In terms of chemistry, I'm talking about bond length. When it is physics, we'll write down here the distance between the two charge. Here the distance is nothing but the bond length. Clear, Madhav, now? Okay. This is the distance, this is the charge. Two factor we have here. Okay. BF3. Do we have net dipole moment in BF3? Could you tell me? The structure is this. BEF2. Do we have dipole moment in BEF2? Just you have to check whether it is 0 or not equal to 0. What is this? What is it, the difference I charge? I didn't get you, Madhav. No, no, no. See, when you have, since we're talking about the bond length, no. So bond length, whenever you have, so the charge will be same, plus and minus, because it is separation of electron. We don't have difference in charge. Okay, so BF3, do we have net dipole moment in this? Yeah, we have electron pair, but we are just talking about this bond here. Okay, you see, this is delta negative, and delta negative, and this one will have delta positive. So positive to negative, we have one dipole moment because of this bond. Here we have dipole moment, and here we have dipole moment. Now this two will have the resultant of this two in this direction, the dipole moment, and this two cancels out each other. So for this one, mu net is equals to 0. Similarly, in BEF2 also, this dipole moment and this dipole moment cancels out each other, and mu net equals to 0. Right? This is what you need to check, whether the dipole moment is 0 or not. You don't have to check the exact value. With this value, we can conclude one particular thing here. When mu net is equals to 0, dipole moment equals to 0, then the molecule is non-polar. Is said to be non-polar. If mu net does not equals to 0, then the molecule is polar in nature. So water, you see, it is polar. This is also polar. Mu net does not equals to 0. This is non-polar, and this is also non-polar. Okay, CHCl3, polar or non-polar? Tell me. CHCl3. CHCl3 is also polar because we have carbon hydrogen, not slightly, carbon hydrogen. We don't consider the electronegativity difference. However, carbon is slightly more electronegative than hydrogen, but the difference is not significant. Okay, but carbon chlorine bond we have polarity, right? And hence the molecule is also polar in nature. CHCl. What about CCl4? CCl4, non-polar. Carbon tetrachloride is non-polar, like CH4. Okay, so this is what you need to just conclude in terms of dipole moment, whether it is polar or non-polar. That is it requires in chemistry. But there are other things also, and that is a part of physics. You will study that in electrostatic in grade 12. CH2Cl2 is polar. CHCl3 is also polar. Okay, you just need to check whether there is any net dipole moment is there or not. Okay, you don't have to bother about the magnitude of dipole moment, whether it is zero or non-zero. That is it. Okay, now the next term we have to discuss here is polarization. Very important term, polarization. First of all, you write down the theory in this. Okay, write down quickly. Whenever a cation approaches an anion, then there is a tendency. All of you copy this down. I'll explain after this. Okay, tendency of distortion of electron cloud. Distortion of electron cloud of anion. This behavior of cation is called its polarizing power. So the term polarizing power we define for cation. That's one thing. Now the tendency of anion to get its electron distorted, is called polarizability. And this phenomenon of distortion of electron cloud is called polarization. Yes. So this is the general thing I have given, Anurag. Did I mention any ion over here? Obviously, there will be less or more distortion when the ions changes. There are factors which affects the polarization. We'll discuss all those things. First, you copy this down. Yes, yes, yes. Electron cloud is the outermost electron cloud for any ion. Done. Okay. So let us understand this. What is this term? Let us understand this. Yeah, I'll send the slides, Suresh. Okay. So you see, suppose we have a cation and an anion present. Okay. So when this cation and anions are close enough, so obviously there will be a natural, no, force of attraction between the two. So what happens? This positive charge attracts this electron cloud towards its side. Okay. So when this attraction is there, now you see at this stage, these are the point charge, you can say, right? Point charge, plus and minus point charge. Now, when they comes closer to each other, or when the attraction between the two takes place, then there will be a distortion in the electron cloud. What kind of distortion? This positive charge attracts the electron cloud towards its side, and this electron cloud starts shifting towards the positive ion like this, right? It goes like this. Right? So it won't be a spherical shape anymore. For this example, I'm talking about, right? So this distortion in the electron cloud, like this, which was spherical initially, now the shape changes like this. So this change in shape is the distortion of electron cloud, correct? So this is the distorted anion, we can say, or distortion. The phenomenon is distortion, or the electron cloud is distorted electron cloud. Okay. So the positive charge which produce this distortion, this positive charge, the ability to produce the distortion is called the polarizability of that particular positive charge ion. Sorry. So the polarizing power of the positive charge ion, and the ability to this electron cloud to get distorted is called its polarizability. Okay. So polarizability is defined for anion, polarizing power is for cation. Okay, there are factors which affects this, and this phenomenon is what is polarization, correct? Now see, if the positive charge density here is more, then this would produce more attraction on the electron cloud and hence more polarization. Yes or no? Tell me. No, positive charge generally for convention, we don't consider that positive charge shift from one place to another place. It is always negative charge or electron. No, it's not photoelectric effect, Shashwat. Okay, so the movement of negative charge always takes place. It's not positive charge. Because positive charge is an assumption we have that there is deficiency of electron, and hence we have the positive charge. Got it? So we don't consider the distortion in positive charge. Correct? Okay, fine. So this is the distortion. So how the distortion get affected by this anion? First thing, when the charge on this cation increases, it produces more polarization. First thing. Second thing, if the charge is same but the size increases, if the size of cation increases, then the charge density decreases, hence polarization decreases because the attraction pull decreases. Right. So all these factors we'll discuss one by one. First, you see, when it was a point charge, when there were no polarization, right, then the bond was completely ionic because you have ionic, electrostatic attraction. But because of this polarization, the electron cloud starts, shifting towards the positive charge, and this shift leads to the covalent character in the molecule. Yes or no? Did you get my point? If there is no charge separation, right, then the bond is covalent. When charge separation is there, it is ionic. Because of this polarization, what happens? This is no longer a point charge now. The electron is shifting towards the positive charge. That leads to what? That leads to covalent character in the molecule. Yes. So more polarization, more will be the covalent character in the molecule. Did you get this point? Very important, this one. Yes. Tell me first. That's why whenever it is ionic, right, there will be a little bit of polarization. Maybe the ionic character is 98%, 99%, but there will be a little bit of polarization. Because of that, we'll have some covalent character. Understood? Right. So this effect, yes, always, always. So this effect, the distortion in the electron cloud, is studied by a scientist called Fajans, and the rule given here by Fajans, we call it as Fajans rule. So all these covalent nature of ionic compound we study under Fajans rule. So write down Fajans rule, the first point here. It explains the covalent character in ionic compound. It explains the covalent character in ionic compound. According to this, covalent character depends upon the following factors. The first one, write down: size of cation. As the size of cation decreases, polarization increases. So size is inversely proportional to polarization. Why this relation we have, I'll tell you here. Suppose we have two, ions, positive ions. One is this, another one is this. So which one has more charge density? For the same anion, obviously. For the same anion we are considering, which one has more charge density? The smaller one, right? The smaller one, and hence it produces more attraction to the negative charge. That's why we have more polarization. Hence, size and polarization are inversely proportional. Size of cation I'm talking about here, right? So here you see, based on this, if I ask you the order of covalent character in this molecule, LiCl, NaCl, KCl, RbCl, which one has maximum covalent character? Okay, so the covalent character is maximum for LiCl because Li is the smallest ion we have, because Cl minus is same in all the molecule, right? So we don't consider this Cl minus effect, the change in covalent character we have because of the cation present into this. Hence we consider the rule of cation here, size of cation. So left to right if you go, left to right if you go, okay, so this side if you go like this, then ionic character increases, character increases. Right to left this side we have polarization increases, and when polarization increases then covalent character increases. Okay, so this is the size of cation. Similarly, the second factor we have the size of anion. It is opposite of the previous one. The size of anion is more than the distance between the positive charge ion, that is cation, and anion decreases, and hence polarization increases. So this is the relation we have. Why this relation we have? Because you see we have a positive charge ion. In fact, two ion we have positive charge of same size, assume the same size, and we have two anion here. One is this, another one is this. So obviously you see the bigger anion has the lesser distance, and hence more will be the electrostatic attraction pull. Hence the size of anion increases, polarization increases. So if I ask you the question here, LiF, LiCl, LiBr, Li, which one has the maximum covalent character? The maximum covalent character we have with maximum size of anion, and this is the answer we have, maximum covalent character. Done. Just a second. Okay, next write down the charge on yes. Aditya, any doubt? Charge on ion, the third factor. Write down as the charge on ion increases, polarization increases. As the charge on ion increases, polarization increases. For example, if you compare NaF and Na2O, sodium has +1, here also +1. Fluorine has -1, here it is -2. So -2 charge on oxygen, hence more polarization, more covalent character. Done? Okay, next write down once again. Write down configuration of cation. Configuration of cation. Write down the cation with 18 electrons the cation with 18 electrons in the outermost shell produces greater polarization than than those of than those of inert gas configuration. Inert gas configuration. For example, if you have NaCl and CuCl, okay, so obviously the charge on Na is plus and Cu is plus. If you look at the electronic configuration of Na plus, it is 1s2, 2s2, 2p6. For Cu plus, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s0 and 3d10. So if you look at the electrons in the outermost shell, because 4s is 0, this is not at all present, right? In the outermost shell is third shell. Third shell has 18 electrons. So the cation with 18 electrons, obviously because we have weak screening effect with D shell, right? So cations with 18 electrons in the outermost shell produces greater polarization. So this one produces more polarization than this, and hence the order of polarization and the covalent bond character is this. Did you understand this? Yes, you can say that. Right. That's the same thing. That is the reason we have. Right? So since CuCl, we have more, excuse me, CuCl, we have more covalent character, and hence the bond is weaker than NaCl. Ionic bond is the stronger bond, right? Because of electrostatic pull. Hence, it is easier to break CuCl. Correct? Okay. This is it. Polarization, the various factor we have discussed. The last point in this chapter we'll see. Write down. Inert pair effect. We have discussed this already. Term we haven't discussed, but reason of this we have discussed. Write down inert pair effect. This is actually observed in group P block elements. So write down in the group 13, write down like this. From group 13 to group 16, as we move down the group, the stability of lower oxidation state increases. The stability of lower oxidation state increases. This is because of from group 16 to group 13 to group 16, from group 13 to group 16, as we go down the group, the stability of lower oxidation state increases, and this is known as inert pair effect. And this is known as inert pair effect. What is the meaning of this? I am taking an example to make you understand this. Group 13 I am taking, right? The lower elements of group 13, we have indium and we have thallium. So what happens in this, the electronic configuration of indium is we have krypton, I said from group 13 to group 16, as we go down the group, the stability of, as we go down the group, the stability of lower oxidation state increases. Stability of lower oxidation state increases, and this is known as inert pair effect. Done? Okay, krypton 4D10, 5S2, 5P1. This is the configuration of India. For thallium, it is xenon 4F14, 5D10, 6S2, 6P1. So the possible oxidation state of group 13 element is +1 if it loses 1 electron from the outermost shell, or +3 if it loses all 3 electrons in the outermost shell. Okay, but what happens as we go down the group, correct? There are weak shielding effect of 4F and D subshell. Because of this weak shielding effect, this 6s electron is strongly attracted towards the nucleus of it. And if you want to remove this electron in order to show +3 oxidation state, you have to provide a lot of energy. So because of this weak shielding effect of 4F and 5D subshell, here we have only D subshell. This also becomes a bit inert towards the reaction, but here to some extent it can show +1 or +3. To some extent it can show. But for this one, it is very difficult to show +3 here. Very difficult to show +3, right? And hence we can say thallium always has tendency to be into +1 oxidation state. That's why it can form TLCl, but TLCl3 is very difficult to form, right? And the stability of TLCl is more than to that of TLCl3. This kind of question they ask here, why TLCl is more stable than TLCl3? Answer is inert pair effect. Why it is inert pair effect? You see this. Because of this weak screening effect of 4F and 5D subshell, the pair of electron present in S subshell, outermost S subshell, becomes inert towards the reaction or bonding. So the pair of electron becomes inert, and hence we call it as inert pair effect. Is it clear? The same thing we can apply for carbon family. SnCl2 is more stable than SnCl4. Oh, I'm sorry. Last element is lead, no. So PbCl2 is more stable than PbCl4. That's why PbCl4 always has the tendency to convert into PbCl2. Right. This is inert pair effect. Is it clear? So with this weak skinning effect, we have discussed 2-3 points here. One is the contraction in size. Okay. We have also discussed this inert pair effect, right? Z effective also we have seen all this. Why it increases. Is it clear? Understood this? Fine. Okay. So this is it for this chapter. Okay. On Learnis, the assignment is uploaded. You can solve those questions. Yesterday, I have sent you 2 PDFs also. That also you can try. Okay. Next class, we'll start with redox reaction. Redox reaction will continue with the mole concept too, because in mole concept too, the concepts of equivalent require the change in oxidation state. How to find out? So to understand that, we should understand redox reaction. So redox reaction is a small chapter. We'll finish that and then we'll move on to the mole concept too. Okay.
Sir.
Clear, guys?
Sir.
Yeah.
So can you just repeat one last time? So why that TLCl3 is very rare, like it's not possible?
TLCl3. See, obviously this, if you TLCl3, if you see, the oxidation state of thallium is +3 here, and here it is +1. Okay. To form this +3 oxidation state, you have to provide a lot of energy to remove this 2 electron here. And hence this is at higher energy state, because you are giving energy to this to remove this 2 electron. And hence higher energy state is the lesser stable state. And hence that
So is
order.
it like if given an option, TL will take +1 oxidation state because that
Right,
one requires less energy.
right.
Okay.
So the question that they frames like this, they'll ask you that why TLCl3 converts into TLCl, or why PbCl4 converts into PbCl2. The answer is because TLCl3, because of inert pair effect, it is not stable, and hence it has natural tendency to convert into a more stable state, that is TLCl or PbCl2. Clear? Yes. चलो ठीक है, थैंक यू गाइस, टेक केयर, बाय बाय.